Good morning. Let's see. So I'm very grateful to the organizers for giving me the opportunity of opening the Strings Conference for the second year in a row. I had a great time on my one previous visit to Seoul in 1997, and I'm delighted to be back. In my opening talk last year in Munich, I attempted to give an overview of the status of the field. There's little that I could add today to what I said then. This time, instead of surveying the field, I have decided to survey a particular topic. So the title, which I haven't revealed until now, is Multi-Charge Superstrings. This is a subject that I worked on in the mid-1990s and have been thinking about again recently. My talk will be mostly a review of some superstring theory basics without a lot of esoteric mathematics. It should be relatively easy for this audience, certainly, to follow. Some of you may already know all that I will say. I think this is a good way to start a conference in which many of the talks are likely to be more challenging. So let me begin by giving away all my secrets. So type 2B superstring theory in 10 dimensions has two distinct string charges, leading to an infinite family of half BPS PQ strings. They form a multiplet of the SL2Z duality symmetry of the theory. I will review basic facts about these strings, as well as the non-perturbative BPS spectrum obtained after compactification on a circle. The dual description in terms of M theory compactified on a torus will also be discussed. Part 2 of this talk examines the so-called 2-0 six-dimensional theories that are associated to a set of separated parallel M5 branes in M theory. Such a theory has a finite set of BPS superstrings which correspond to the roots of a simply laced or ADE type Lie algebra. In both the 10-dimensional and 6-dimensional settings, there are 3 string junctions that can be used to build string networks. The 6-dimensional strings and string networks provide an effective way of characterizing BPS brane configurations on the Coulomb branch, and also in lower dimensions after compactification on a circle or a torus. There will be additional talks about the 2-0 theories at this conference, given by Michael Douglas and Seok Kim, and Sungjae Lee might also discuss aspects of these theories in his review talk. I expect these speakers, and possibly others, to explore the subject in greater depth than I will. So let me begin with the duality relating M theory to type 2B superstring theory. One of the dualities discovered in the 1990s relates M theory compactified on a torus to type 2B superstring theory compactified on a circle. I will now describe how the parameters associated with each of these are related. So let us first denote the Planck length for M theory in 11 dimensions by L sub M, and the Planck length for type 2B superstring theory in 10 dimensions by L sub B. The latter is related to the string scale L sub S and the string coupling constant G sub S by the formula shown. LB is G string to the 1/4 times L string. The type 2B theory has a discrete SL2Z duality symmetry under which the complex scalar field lambda transforms in the usual nonlinear manner. In other words, lambda goes to A lambda plus B over C lambda plus D, where the matrix ABCD is an element of SL2Z. C0 is the Ramon-Ramon scalar field in the 2B theory, and phi is the dilaton field. Let us denote the expectation value of lambda by tau sub b. So it has a real part, which is an angle, theta, and an imaginary part, which involves the string coupling constant, which is the expectation value of e to the dilaton. The Einstein frame metric of the type 2B theory is SL2Z invariant, and hence the Planck length L sub B is also SL2 invariant, but the string scale L sub S is not because the coupling constant G sub S transforms under SL2Z. So we will characterize the M-theory torus by a modular parameter tau sub M and an area, which I write as 2 pi squared times A sub n. This will avoid factors of 2 pi in later formulas by making this definition. The type 2b circle has radius r sub b. Now the crucial fact about the duality between M theory and type 2b superstring theory is that the SL2Z duality group of the type 2b theory is identified with a modular group of the M theory torus. And therefore the parameters that I called tau sub m and tau sub b should be identified. And henceforth I will just use the symbol tau to refer to either one of them, with a real part tau 1 and an imaginary part tau 2. Further relations are obtained by identifying dual half BPS brane configurations and equating tensions. To do this, we need to recall that the tensions of the supersymmetric M-branes are given by the formulas shown. So the tension of the M2 brane is proportional to 1 over the Planck length cubed on dimensional grounds, and the tension of the M5 brane is proportional to 1 over the Planck length to the 6th power, again on dimensional grounds. Also, the tension of the type 2b D3 brane is given by an SL2Z invariant formula. It's usually written in the first form where you see a factor of 1 over the string coupling constant in the denominator, as always occurs for D branes. But when you rewrite it in terms of the Planck length, the string coupling constant disappears, and it's manifestly SL2Z invariant, since, as I already pointed out, the Planck length is SL2Z invariant. So to go further, we will match branes in the different theories, and by wrapping on various cycles and equating tensions. So we will first consider matching 3 branes, and to do this, we consider the tension of a D3 brane, and we will equate it or identify it with an M5 brane wrapped on the torus. So when we wrap the M5 brane on a torus, we see an object with 3 spatial dimensions in the remaining 9 dimensions. And this identification, just writing the wrapped M5 brane as having a tension given by the area of the torus times the tension, after you invert the formula, gives the relation between the parameters that's shown. Similarly, identifying an M2 brane with a D3 brane wrapped on the circle of radius r sub b gives another similar formula relating these parameters. Now these 2 formulas can be combined to relate dimensionless quantities. So in the formula on the bottom of the slide, we have a dimensionless measure of the area of the torus raised to the 3rd power related to a dimensionless measure of the radius of the type 2b circle raised to the -4 power. And so this shows you how the area goes to 0 as the radius goes to infinity, and vice versa. Now it's also interesting to identify the 1 branes, the BPS 1 branes in the 2 descriptions. So the type 2b theory has an infinite spectrum of half BPS PQ strings in 10 dimensions, which can be regarded as bound states of P fundamental strings and Q D strings. The integers P and Q measure the strengths with which the strings couple to the 2 forms B sub 2 and C sub 2 in the type 2b supergravity multiplet. So I remind you that the B field is in the NS-NS sector and the C field is in the RR sector. The PQ strings are stable whenever P and Q are co-prime. The PQ string tensions are given by the formula shown. So the tension of a PQ string is the absolute value of P plus Q tau times the tension of a fundamental string. Clearly that factor should be the fundamental string because the fundamental string has P equal to 1 and Q equal to 0. The tension of the fundamental string is given by 1 over 2 pi times the string length squared, the string length scale squared, but that can be rewritten in terms of the Planck length in the second form shown. So when you look at the formula for T sub PQ here, it involves a tau dependence which has this absolute value divided by the square root of tau 2. And that's the correct tau dependence that's required for the string charges P and Q to transform linearly as a doublet under the SL2Z transformations. And this is required because the two fields B sub 2 and C sub 2 also transform as a doublet. The dual description of the PQ strings in 9 dimensions is given by wrapping one dimension of an M2 brane on a geodesic curve in the PQ homology class of the torus. And the length of such a cycle is given by the formula shown. Multiplying this length by the tension of the M2 brane and using previous identities that I showed gives the expected result T sub PQ, so verifying the correspondence. So next I want to turn to matching the BPS zero branes, or point particles. And this analysis is more involved and more interesting, really. So let us start with the two simplest cases, which are the half BPS cases. So an M2 brane wrapped k times on the torus is dual to k units of Kaluza-Klein excitation of the type 2b circle. And this gives half BPS states with mass in terms of the wrapping. So using the fact that you have wrapped M2 branes, you deduce that the mass should be this. And on the other hand, since there are Kaluza-Klein excitations on the circle, the mass should be this. And the agreement of these expressions is a consequence of previous formulas. Now the little group that classifies massless excitations in d dimensions, which is spin of d minus 2, is the same as the one that classifies massive excitations in d minus 1 dimensions. Therefore, each Kaluza-Klein excitation of a 10-dimensional massless supermultiplet on a circle is a massive supermultiplet in 9 dimensions that is group theoretically identical to the massless one in 10 dimensions in terms of its spin content. Thus, the preceding half BPS states, which are Kaluza-Klein excitations of the type 2b supergravity multiplet, are massive chiral multiplets in 9 dimensions. In particular, each of them contains 2 massive gravitinos of the same chirality. There isn't much discussion in the literature of the fact that massive states can be chiral, but it's certainly the case. A second class of half BPS zero branes arises from a PQ string wrapped W times on the type 2b circle. This is dual to an Kaluza-Klein excitation with integers n1 and n2 on the M-theory torus. And the masses can again be computed in the two dual manners. So in terms of a wrapped string, we just have the circumference of the circle, we just have the circumference of the circle, 2 pi r, times the number of times the string wraps times the tension of the string. And then that's equated to the formula for Kaluza-Klein excitation masses on the torus with modular parameter tau and area a sub m. And these two expressions agree using previous identities, provided that we make the identification that the pair of integers n1 and n2 correspond to w times p and w times q. Since p and q are co-prime, this means that w is the greatest common divisor of n1 and n2. In this case, the massive supermultiplets in 9 dimensions are identical to massless 10-dimensional type 2a supergravity multiplets, so they are non-chiral. To summarize, we have learned that there are 2 distinct classes of half BPS zero brane massive supermultiplets in 9 dimensions, chiral ones with mass m sub k, and non-chiral ones with mass m sub n1, comma, n2. Supersymmetric zero branes in 9 dimensions that carry both types of charges can only be quarter BPS. So let's now examine them. A type 2b superstring on a circle with winding number W and Kaluza-Klein excitation number K satisfies the level matching condition that NL minus NR is WK, where NL and NR denote excitation numbers of left-moving and right-moving oscillators in the usual way. String excitations that have either n left equal to 0 or n right equal to 0 will be quarter BPS. Because of the SL2Z symmetry and supersymmetry, this statement applies to all of the PQ strings, not just the fundamental string. So let's look at the masses of these quarter BPS zero branes. And it's easy to read off from the standard formulas that the mass for the zero branes that carry all 3 charges, K, N1, and N2, is just the sum of the previous masses that we obtained for half BPS states. Now for large N, remember N was the oscillator excitation number and was identified as W times K, the number of quarter BPS states is roughly given by the exponential of 2 pi square root of n by the standard formulas for the number of states of a string at large excitation number. If there is to be a black hole interpretation of these zero branes, these quarter BPS zero branes, the entropy S should be 2 pi times the square root of WK, the logarithm of the degeneracy. Since W is the greatest common divisor of N1 and N2, it jumps around wildly as the charges N1 and N2 are varied, even though the mass does not. This is a disturbing result if one expects to find a macroscopic geometric description of these quarter BPS states in terms of black holes. The basic problem is that the charges N1 and N2 transform as a doublet of SL2Z. And the greatest common divisor of these integers, W, is the only group invariant that can be constructed out of such a doublet. Therefore, any improvement of the formula for the entropy, such as including contributions of multi-centered configurations, would still have to be a function of W, and therefore it would have the same problem. One way of avoiding this conclusion, and the only one that I can think of, is to suppose that these quarter BPS states do not exist. This is plausible because they are at threshold for decay into a pair of half BPS states. The existence or non-existence of threshold bound states is always a subtle matter. The half BPS states do not require a macroscopic geometric description since they're just a fixed finite number of them. This problem does not arise for the familiar 4-dimensional and 5-dimensional examples of supersymmetric black holes. In those cases, there are more duality group invariants, and the leading term in the entropy respects the continuous group symmetry, not just the discrete one. So let me now talk about string junctions. The PQ strings can form 3 string junctions, and the rules are quite simple. The string charges should be conserved at the junction, just like momenta at a vertex in a Feynman diagram. The angles between the strings at the junction are determined by requiring the forces given by the string tensions to balance at the junction. One can use these junctions to build up string networks. The 3-string junction is quarter BPS, and the same is true for any string network that's in a 2-dimensional plane. By studying string networks with the external strings ending on D3 branes, one can carry out detailed explorations of the spectrum of 4-dimensional maximal super Yang-Mills states that preserve various amounts of supersymmetry. I'm using the notation MSYM here for the in 4 dimensions, for where I in the past have always referred to it as n equal 4 super Yang mills. Only half BPS states can occur in the SU2 theory, since there are just 2 D3 branes, and therefore all the string configurations would be on a line. States with less supersymmetry occur in all of the higher rank theories. Last year, Ashok Sen gave a detailed discussion of quarter BPS states in 4-dimensional MSYM theories based on string networks, and in particular, he gave a very intuitive description of the origin of wall crossing phenomena. Let me now say something about branes within branes. Sometimes we are interested in considering BPS branes that contain lower dimensional branes embedded within them in such a way that the charge of the lower dimensional brane is uniformly distributed within the higher dimensional brane. In some cases, the smearing of the charge can be interpreted in terms of localized objects from a higher dimensional viewpoint. I will give 2 examples, but there are quite a few others. So we'll start with strings. So let us begin with a half BPS PQ strings in 9 dimensions. A more general possibility, which is still half BPS, is for the 10-dimensional PQ string to wrap the circular dimension in a helical manner, like in a solenoid. In other words, the string has a constant winding number per unit length. Such a string is a straight line in the covering space, and therefore it's clear that the string is still half BPS. From the 9-dimensional viewpoint, this produces a PQ string that also has finite charge densities, rho 1 and rho 2, where rho is, which is equal to rho times the PQ vector. By computing the 10-dimensional length of the string, it is easy to deduce that the apparent tension of the string in 9 dimensions is given by the formula shown. So this formula involves the tension of the PQ string without the additional densities of rho 1 and rho 2. And then the second term involving the density rho is given here, where m is the mass of the PQ D0 branes that I discussed earlier. A similar construction can be carried out for the D3 brane. If one of its dimensions is wrapped helically on the 2B circle, this results in a half BPS D3 brane in 9 dimensions with a density rho sub m2 of m2 brane charge. It may sound funny to refer to M theory in discussing type 2B theory, but this is the dual interpretation that we had. The resulting tension of the D3 brane from the 9-dimensional perspective is the usual tension squared plus the contribution from this M2 brane charge embedded in it. In 9 dimensions, D3 brane charge and M2 brane charge are electric magnetic duals. Thus, this D3 brane carries mutually non-local charges. This is a consequence of the self-dual charge of the D3 brane in 10 dimensions. So I finished the first half of my talk, more or less on time, and now I want to turn to the 2-0 theories in 6 dimensions. It's an important challenge to develop a useful formulation of the 2-0 6-dimensional superconformal field theories associated with multiple coincident M5 branes. These theories, which have an ADE classification, seem to be the most fundamental of all non-gravitational relativistic quantum theories. Many interesting theories in lower dimensions, as well as relations among them, have been characterized in recent years in terms of compactifications of these theories, and this has been very fruitful. This problem is related to the even more fundamental problem of constructing a non-perturbative formulation of M theory or superstring theory. The relation is apparent, for example, when one considers the ADS-CFT duality that relates M theory on ADS 7 times S4 with n units of 4-form flux to the A sub n minus 1 2-0 superconformal field theory. This is a great correspondence, but both sides still need to be understood better. A wide range of approaches to understanding the 2-0 theories have been explored, and some of them will be discussed by other speakers. I will describe and elaborate upon a proposal that I made in 1996, and I will also refer to recent work of our distinguished chairman, Kim-Young Lee, and his collaborator, Mr. Yi, in 2006. The focus will be on identifying the BPS excitations that are present on the Coulomb branch. A basic fact about M5 branes is that M2 branes can end on them, much like fundamental strings can end on D branes. When an M2 brane is suspended between a pair of parallel nearby M5 branes, it can be approximated by a superstring within the six-dimensional world volume theory of the M5 branes. The string tension is the separation of the M5 branes times the M2 brane tension. This is analogous to the 10D superstring suspended between a pair of parallel D3 branes. And this analogy suggests that the BPS branes in the world volume theory of a set of parallel flat M5 branes should include these strings. Note that the 10-dimensional strings that enter the D3 brane analysis are transverse to the branes, whereas the 6-dimensional superstrings that enter in the M5 braner analysis are along the branes. So let me remind you of the 2-0 tensor multiplet. The world volume theory of a single M5 brane has two six-dimensional supersymmetries of the same chirality. This is analogous to the type 2b string theory in 10 dimensions. In addition to six-dimensional super-Poincare symmetry, the M5 brane theory has a spin 5 or equivalently USP of 4 R symmetry, which corresponds to rotations of the 5 spatial dimensions that are transverse to the branes. The superconformal symmetry that incorporates and extends these symmetries is the famous supergroup OSP 6,2/4. The massless tensor multiplet associated with a single M5 brane consists of a two-form field B with a self-dual field strength, 4 symplectic Majorana chiral spinners, and 5 scalars. In terms of the six-dimensional little group, which is SU2 times SU2, the covering group of SO4, the representations are 3, 1, which is the self-dual two-form field, and 4, 2, 1, which are 4 of these symplectic Majorana spinners, and 5 scalars, 1, 1. The coefficients 1, 4, and 5 are the dimensions of irreducible representations of the R symmetry group. So that's the tensor multiplet. So now let's look at the six-dimensional superstrings. We can identify the BPS branes of a six-dimensional 2-0 theory that correspond to n parallel M5 branes whose positions y sub I are distinct but otherwise arbitrary. So these y sub i's are 5 vectors in the space transverse to the branes. There are n(n-1/2) oriented half BPS strings in the six-dimensional theory, and they correspond to M2 branes stretched between each pair of M5 branes. So if they have labels I and j where I is less than j, that accounts for this number. Interchanging I and j would correspond to reversing the orientation of the string. The tension of the IJ string is proportional to the distance that the M2 brane is stretched, which is just given by this formula here. The zero modes of each superstring form a 2-0 tensor multiplet in 6 dimensions. The supermultiplet that is the zero mode of the IJ string contains the difference BI minus BJ, where BI is the self-dual tensor field on the ith M5 brane, and BJ is the self-dual tensor field on the jth M5 brane. And the IJ string is also a source for that same field, BI minus BJ. In terms of physical degrees of freedom, the tensor supermultiplet arises from tensoring left-moving and right-moving zero modes of the string. And these zero modes must be, and I could argue why, but I won't, must be given by a doublet. So a doublet of the left-handed SU2 and then two singlets. And so you tensor this factor as the zero modes of the right movers times this as the zero modes of the left movers, and then you find precisely the tensor multiplet that I described earlier. This is analogous to the way one forms the type 2b supergravity multiplet out of the type 2b superstring theory zero modes in 10 dimensions. However, there are a few important ways in which the 6-dimensional 2-0 superstring theories differ from the 10-dimensional type 2b superstring theory. The 6-dimensional theories have n times n minus 1 over 2 distinct oriented superstrings, whereas type 2b theory has an infinite number of distinct half BPS superstrings, the PQ strings that we discussed earlier. Also, the 6-dimensional superstrings carry n minus 1 distinct charges, whereas the PQ strings in 10 dimensions carry 2 charges, P and Q. More generally, the number of charges is the rank of the Lie algebra, and the charges of the strings correspond to its root vectors. Each B field has a self-dual field strength, which implies that each 6-dimensional superstring is self-dual. This is not analogous to strings in 10 dimensions, but it's analogous to the D3 brane in 10 dimensions. The 10-dimensional fundamental string has a weak coupling limit. And one could, in fact, define weak coupling limits for any of them because they're all equivalent. And this makes it possible to study the type 2b superstring theory perturbatively. The 6-dimensional 2-0 theories, on the other hand, do not have a weak coupling limit. So that's an important difference. Since there's no weak coupling limit, there is not much to be gained from studying the excited modes of a free string. If one could identify circumstances in which excited string states are supersymmetric or long-lived, then this information would be useful. Infinite straight strings, which are stable half BPS objects, are sensible objects to consider. Since they are infinitely long, they carry infinite energy as well as a conserved string charge. When these strings wrap compact dimensions, their energy is finite, and more of their properties become relevant. So let me just remind you of the type 2b interpretation of the origin of 2-0 theories. In this geometric engineering approach, you can give an alternative description of the 6-dimensional 2-0 theories in a type 2b setting. So suppose that 4 dimensions of type 2b superstring theory form an so-called ALE space, asymptotically locally Euclidean space, which is a non-compact hyperkähler manifold of 4 real dimensions, which I'll call Y. For example, the AN-1 case is given by the hyperkähler resolution of the orbifold C2 mod the cyclic group Zn. The corresponding 6-dimensional 2-0 theory decouples from the rest of the type 2b dynamics because the ALE space is non-compact. Such a space contains a collection of 2 cycles which correspond to the positive roots of an ADE Lie algebra. When the 2 cycles collapse to a point, they give a singularity of ADE type. On the Coulomb branch, all the 2 cycles have finite size. Since A sub n-1 has nn-1 over 2 positive roots, this is the number of 2 cycles. D3 branes wrapping these 2 cycles are the 6-dimensional superstrings we have discussed. So rather than thinking of these strings as stretched M2 branes, we have this dual interpretation as D3 branes wrapping 2 cycles. n-1 of these 2 cycles correspond to the simple roots of the Lie algebra, whose intersection numbers are encoded in the Dynkin diagram of the Lie algebra. The decoupling of the center of mass tensor multiplet in the M-theory analysis. Remember, we only had differences, Bi minus Bj, appearing in the zero modes. So there was an overall B field in tensor multiplet that decoupled in the M-theory analysis. But that's not an issue in this approach because in the type 2b picture, it doesn't occur in the first place. And therefore, it doesn't need to be decoupled. A related problem in which gravity is not decoupled is K-theory compactified, is a K3 compactification of the type 2b superstring theory. In that setting, there is a big duality group, SO21, 5 over the integers, and the strings can carry 26 different charges. So these are really multiple charge strings. The duality group that relates these strings that arises from, the duality group relates the strings that arise from D3 branes wrapping 2 cycles to the unwrapped PQ strings. And this suggests that their properties are closely related. But I won't pursue that here. Rather, let me consider the simplest example, the A1 theory, so A1 is the Lie algebra of SU2. And we'll compactify on a circle to make contact with the maximal Super-Yang-Mills theory in 5 dimensions. So we consider compactification of the A1 2-0 theory on a circle of radius r. So this is expected to give 5-dimensional SU2 maximal Super-Yang-Mills with a coupling constant G Yang-Mills squared that's proportional to the radius of the circle. The 5-dimensional Super-Yang-Mills theory has recently been shown to be UV divergent at 6 loops. Heroic analysis by Baron et al., which appeared last year. In principle, the 2-0 construction provides its UV completion, even though the Super-Yang-Mills theory by itself is non-renormalizable or not non-finite. So let us examine whether we can account for all the BPS particles and strings that are expected in the 5-dimensional maximal Super-Yang-Mills gauge theory. Massless particles or fields arise as the dimensional reduction of the massless tensor supermultiplet in 6 dimensions. So this gives a massless vector supermultiplet in 5 dimensions. The little group in 5 dimensions for the massless state is just the diagonal subgroup of the SU2 times SU2 that you have in the 6-dimensional case. Supersymmetric massive states can arise as string winding modes or as Kaluza-Klein excitations. And these are both half BPS. And just as in 9 dimensions, there are 2 different half BPS massive supermultiplets in 5 dimensions. The massive little group in 5 dimensions is the same as the massless one in 6 dimensions, namely SU2 times SU2. So the Kaluza-Klein excitation massive supermultiplets are identical to the 6-dimensional massless tensor multiplet, and therefore have the content 3, 1 plus, so here's their content, just as for the massless tensor multiplet in 6 dimensions. So these are chiral massive multiplets. The winding supermultiplets, on the other hand, are non-chiral. Just as in 10 dimensions, the relative chirality of the left movers and right movers is reversed for winding states. And that yields the field content that you get by tensoring this with this, where I've just reversed a 2-1 to a 1-2 here. And that produces this set of fields, which happens to be the same as a massless vector supermultiplet in 6-dimensional maximal Super-Yang-Mills. But that's just has no deep significance. The winding number W is a gauge charge, since it couples to the massless vector field. The choices of winding plus or minus 1 give the charged members of the broken SU2 gauge multiplet. And they are often referred to as W particles. So we're just dealing with an SU2 theory on the Coulomb branch. And these are the massive gauge particles. And the fact that they're called W particles is fortuitous because in this description they're arising as winding states, which I've represented as W also. So the mass of a winding state is the distance of the winding, 2 pi r times the winding number, times the tension of the 6-dimensional string. And winding states with winding number greater than 1 would give multiply charged particles. And these are things we certainly do not want in our spectrum, since an SU2 gauge theory has W plus and W minus, but it doesn't have W plus plus and W minus minus and so forth. So the conclusion is that such states are a threshold for decay into singly charged particles, and therefore only the winding number plus or minus states, plus or minus 1 states, should exist. The ones with multiple windings should not exist as bound states. Suppose we compactify on a torus instead to make contact with 4-dimensional maximal super-Yang mills. Then the winding the string on a PQ cycle of the torus gives a half BPS dion with electric charge P and magnetic charge Q and a mass given by this formula. This is the same formula we encountered previously for the tension of a PQ string in 9 dimensions, interpreted as a wrapped M2 brane. As in that case, P and Q are co-prime and transform as a doublet of the SL2Z duality group. In a dual interpretation, the 4D dions arise from PQ strings stretched between 2 3 branes. So let me return to the 5-dimensional analysis. I won't say anything more about 4 dimensions. The Kaluza-Klein charge K is associated to a global U1 symmetry, since this is not a gravity theory. We're used to think of Kaluza-Klein charges as gauge charges, but that's because we're working in the gravity context, and the gauge field comes out of the higher dimensional gravity field. But here we don't have gravity, so it's only a global symmetry. The masses of the Kaluza-Klein states are K over R, and they correspond to what you might call instanton particles in the 5-dimensional gauge theory. Classically, the 5-dimensional gauge theory in the unbroken phase has standard multi-instanton solutions that utilize the 4 spatial dimensions for the construction. So unlike the usual instantons in 4 dimensions, there's no Euclidean continuation here. We're using the 4 dimensions that are already Euclidean, even when the 5 dimensionals are Lorentzian. So roughly, these Kaluza-Klein states correspond to normalizable harmonic forms on the instanton moduli spaces. In a type 2A interpretation, they are the D0 branes inside D4 branes. Now, an obvious question is whether there are quarter BPS 0 branes that carry both W charge and K charge. So these would satisfy the formula of the type N equal WK, where N, remember, is an oscillator excitation number, W is the winding number of the string, and K is the Kaluza-Klein excitation number. In the 9-dimensional case, I argued, based on black hole considerations, that these states should not exist. However, that argument doesn't apply here because this is not a gravity theory, and so there are no black hole considerations. If these states do exist in 5 dimensions, then the details of the spectrum of string modes would become relevant. Now, Kim et al., a group of 6 of you here, computed an index in 5-dimensional maximal super-Yang mills that encodes properties of such states. And this paper found a rich spectrum implying that these states do exist. But so far, they did not give a simple string interpretation of their results. Finally, there is the original 6-dimensional superstring itself, now in the 5-dimensional theory. It couples magnetically to the massless vector field. This string is described in the gauge theory on the Coulomb branch by the Atuf-Polyakov monopole construction, and it extends as an infinite line along the spatial direction that is not utilized in the construction. This string can also be wound helically around the circle that we've compactified in getting from 6 dimensions down to 5 dimensions. In this case, it carries an electric charge density ρ per unit length, which makes it dionic with 5-dimensional tension given by a formula similar to those that I discussed previously for branes within branes. In 2006, Kim-Young Lee and Yi generalized the monopole solution of the gauge theory to account for this additional charge density on this ionic string. So these things are understood from a gauge theory viewpoint. Now, Lee and Yi also observed that the 6-dimensional superstrings can form 3-string junctions. The strings at a junction are the strings associated with the 3 pairings of any 3 of the M5 branes. Moreover, in 5 dimensions, there can be 3-string junctions of dionic strings. String junctions span a plane if the 3 M5 branes are not collinear, and the configuration is quarter BPS. The junctions can be combined to build up complex networks, both planar and non-planar. In the n-1 case, the number of distinct string junctions is given by triples of n of the M5 branes, so that gives you the combinatorics shown. The factor of 2 that I pulled out front accounts for the reversal of the orientation of the strings at the junction. Now, one of the challenges in this business is to account for the number of degrees of freedom that's predicted by the dual ADS construction. And in the case of the A-20 theories, A-type 20 theories, the ADS prediction at leading order in n is n cubed over 3. And so in 2011, Bolognesi and Lee observed that this corresponds to the number of 3-string junctions. In fact, they also pointed out if one adds an n-1 as the contribution of individual strings, then subleading powers of n also agree. Now, there's an anomaly-based derivation of the number of degrees of freedom that I find more compelling. However, if this argument is correct, the explanation in terms of strings and string junctions has the virtue of identifying the degrees of freedom that are being counted. I think it's tempting to speculate that there may be an associated algebraic structure to be elucidated. So I'm nearing the end, so let me conclude. The duality between type 2b superstring theory compactified on a circle and M theory compactified on a torus has interesting implications for both theories, and it provides useful tools for studying theories associated with multiple parallel branes. Even though the 2-0 superconformal field theories in 6 dimensions interact strongly, one can identify their BPS branes on the Coulomb branch. These consist of massless tensor multiplets and half BPS strings, as well as string junctions and networks. The conformal limit in which the M5 branes become coincident and in which the strings that arise from stretched M2 branes become tensionless still needs to be better understood. I don't think the literature yet gives a good understanding of what it means to have a tensionless string. So I think that's a challenge that needs to be addressed. So I'm looking forward to an exciting conference, and I thank you for your attention.